And hello everyone. Today I'm going to present our work on CellReplay, which is our take on making record and replay for cellular network even more faithful. And this work is done in collaboration with Bala from VU Amsterdam, my advisor Brighten Godfrey, and Haitham from EPFL. Okay, so there are so many applications that we use in a daily basis that run on cellular networks. And looking ahead, cellular networks are going to support emerging applications like AR/VR and self-driving cars. Therefore, as an application developer, it is important to understand how your application performs over cellular networks. For example, imagine that you are a developer or researcher working on a new video streaming protocol or algorithm. You'd want to see how your streaming algorithm performs over 5G. You also want to know how it compares compared to the previous ones. On top of that, you want to test your algorithm under interesting real-world conditions. Well, for example, you may want to see how your algorithm performs in the challenging conditions like in a basement or in a crowded stadium, or even under various device mobility such as walking or driving. There are also other combinations of different technologies and network operators that you want to test. The gold standard for testing is, well, of course, to run your application over live cellular networks. You can test it on 5G and evaluate its performance directly. However, this becomes challenging in the early stages of development, especially when you want to test scenarios involving mobility. But what I think is the most important issue is that the lack of control over cellular network conditions make it difficult to reproduce results and debug performance issues. Therefore, researchers and developers often use trace-based network emulators. This process involves recording network traces under specific conditions of interest, such as walking or driving, using a specific predefined workload. And after that, the traces are replayed through the emulator interface, and any desired application can just use this interface. And we refer to this method as the record and replay network emulator. The state-of-the-art approach and the most popular method is to record packet propagation delay and packet delivery opportunities, and then replay them in Mahi-Mahi network emulator. This record and replay approach was actually introduced by CellSim, but I will just refer to this whole approach as Mahi-Mahi, as it is the more well-known system. This method has been very useful and is widely used, especially by researchers like us. As you can see here, there are plenty of papers, even from last year, that use Mahi-Mahi. So how are network traces collected in Mahi-Mahi? First, we measure the packet propagation delay using a packet probing tool like ping. Specifically, we want to measure the minimum RTT of a packet and divide it by 2 to get the one-way propagation delay. Then, we need to record a PDOs using a saturator workload. This workload saturates the link by sending packets beyond the maximum throughput. And the goal is to keep the buffer occupied all the time. And then the receiver notes how each packet is received. Specifically, we record the timing between packets and how each one arrives compared to the first. We call this collection of timestamps as the packet delivery opportunities, which is basically just a schedule for how cellular network deliver packets. Other than just showing the packet schedule, PDOs also emulate varying link bandwidth, but on a finer grained packet by packet level. After collecting those traces, we can put them in the Mahi-Mahi emulator such that application traffic will be delayed by a fixed propagation delay and will be released based on the PDO schedule. Well, I personally use this record and replay approach for my research, where I recorded network traces this way and tested my application in the Mahi-Mahi emulation. Well, however, I was surprised to find that applications running on Mahi-Mahi tend to have different performance results when compared head-to-head compared to the live network counterpart. For instance, in web browsing application, pages load faster compared to live network. Files are also downloaded faster than it should. And in video streaming, the bit rates reported in Mahi-Mahi are higher than those on the live network. And more importantly, we also found that these discrepancies also affect the protocol evaluation result. Okay, so before we dive into the root cause, I want to present the roadmap of this talk. First, I'll discuss what are causing this error and present insights that we discovered from real 5G measurements. Then we'll present our system, CellReplay, to address those issues. And finally, we present the evaluation of CellReplay. So, what went wrong? Well, in general, there are two critical elements in network emulation. The first one is the base packet delay, and the other is the available bandwidth on that link. The first issues that we discovered is that Mahi-Mahi type approach fails to capture the variability of the packet space RTT, which is the packet RTT without any self-inflicting queuing delay. Mahi-Mahi emulates packet delay using a combination of fixed propagation delay and delay introduced by the PDO schedule. However, this combined delay does not fully capture variability. In fact, we found that Mahi-Mahi underestimates packet RTT, and the overall RTT distribution is also not visibly different compared to the live 5G. To address this issue, well, our solution is pretty straightforward. We just record the packet-based delay over time and replay it during the emulation. However, we found a second issue that is more fundamental and challenging. In cellular networks, especially on the downlink, we discovered that the PDOs, or the available bandwidth, depends on the user workload. Well, this was unexpected because in wired networks, the available bandwidth is typically given and doesn't change based on what the user is doing. The major impact for this is that flows running in Mahi-Mahi tend to complete faster than they should compared to live 5G networks. So, how do we tackle this problem? Well, this is a challenging problem to solve, as remember, the whole point of record and replay is to record one trace and replay that trace under a variety of applications. If the trace depends on the workload, is it feasible to do the record and replay? To find a viable approach, we have to understand the dependency between the PDOs and the user workload first. So we conducted experiments in which our server periodically sent trains or bursts of UDP packets every 100 milliseconds. We also varied its train size, that is, the number of packets within each train. Our goal was to measure the average throughput experienced by the different train sizes. Here are the results for T-Mobile and Verizon. The x-axis here represents the train size, and the y-axis shows the experienced throughput. And as you can see, different train sizes result in different rates, with smaller trains or lighter workloads experiencing lower throughput compared to the larger one. And for reference, this is the throughput reported by the saturated workload, which is higher compared to all the others. As you can see in this graph, it is clear that cellular providers allocate delivery rates differently for light packet train probing kind of workloads and heavy workloads like saturator. To gain a deeper understanding, we want to reveal the PDO or packet delivery opportunities pattern that different train sizes report. Here, the PDO is a arrival time of each packet in the train relative to the first packet. And our goal here is to plot the PDOs in this graph, where you can see when each packet in the train is delivered relative to its first packet. This is the result that we get for a train size of 200 packets. We call this as a PDO line, and this line reveals the delivery schedule of each 200 packets in a train. Here are the PDO lines for other train sizes. Well, as you can see in the figure, T-Mobile and Verizon both have completely different PDO pattern. However, when I added the saturated PDO line in the picture, you can see that as the train progresses, the PDO rate is more closely aligned with the saturated rate. Note that because this is a plot of arrival time, packet arrival time, the slope of the PDO line indicates its PDO rate. So another key point that we observe here is that as the workload becomes much heavier, its PDO rate becomes closer to the saturator. So how should we approach the PDO workload dependency problem? Our main key idea is to record PDOs using multiple workloads simultaneously and then interpolate during replay. Well, we have this kind of limitation where we want to record only with limited amount of workload, as we still want to preserve the simplicity of the record and replay. So our solution is to just record with two workloads, light and heavy, chosen at the extreme of traffic pattern. And this is based on the observation that smaller trains or lighter workloads and saturated or heavy workloads are given different rates of or PDOs. And as the workload becomes much heavier, the rate gets closer to the saturator. Thus, we use packet train probing to record the light PDOs, and similar to Mahi-Mahi, we also use saturator to record the heavy PDOs. Then we need to interpolate between these two PDOs during replay. And interestingly, by just adding one additional workload for the recording, which is the light workload, we managed to reduce the emulation error from 18.77% to 5.68%. So how does PDO interpolation work? Suppose that we use a packet train size of 100 to record the light PDOs. This will be its PDO line. We also record the heavy PDOs as captured by saturator, and the dotted line here is the heavy PDOs line. For the replay, we will use these PDOs for the first 26 milliseconds or until the PDO runs out. Then we will splice into the saturator PDOs for longer packet sequences. And then we'll return to the light PDOs after the queue is empty for F milliseconds. Then the next question will be what train size should we use and how to determine the F timer. All those parameters will be determined in the calibration phase, which includes series of automated tests. You can find more details in our paper, but in high level, we want to find a train size with the least interpolation error. To the end, we introduced CellReplay, a record and replay framework for cellular network emulation. The goal is to ensure that applications will perform similar on CellReplay as it is performed on the live network. We also want to record traces once and use it for any applications. There are three processes of using CellReplay. When recording network traces in a specific environment, we first perform an automated calibrations of parameters in that environment. And then we start recording live traces by running the workload itself. And then the traces are then used to emulate the network during the replay. To record the traces, we use two phones to run saturator and packet train echo workloads simultaneously. The packet train echo will record the base packet RTT and the light PDO trace. The saturator will record the heavy PDO similar to Mahi-Mahi. Then we can fit those traces into an emulated network interface such that any packets will experience a base delay according to the time-varying traces and released based on the interpolated PDOs of the light and heavy as I've shown previously. To evaluate CellReplay, our main question is how accurate is CellReplay in replicating application performance compared to the live networks and Mahi-Mahi. We tested various applications including web browsing, TCP file downloads, and video streaming. We also performed the evaluation under diverse conditions that also includes mobility. This is our setup. We connect a laptop with two phones, and it can send a traffic to our server, which is running a server application. And all of our experiments are conducted in a randomized trials, in which we perform series of randomized actions that includes record traces according to CellReplay or Mahi-Mahi, and run tested applications over the live network. The collected data for this setup is the network traces for CellReplay and Mahi-Mahi, and also the ground truth data of the application performance. This is our emulation setup. We use the same laptop and server and connect them over a network emulator with either CellReplay or Mahi-Mahi traces. The collected data here is then the application performance running on CellReplay or Mahi-Mahi emulation. Then we compare the application performance distribution when running over the live versus the emulation. Specifically, we measure the average distance within the two CDF and divide it by the mean of the ground truth to get the emulation error. This is the overview of the results of the CellReplay accuracy and its variant when replicating web browsing performance in HTTP1, HTTP2, and downloading file size with different sizes. Mahi-Mahi used a fixed propagation delay and heavy PDOs, and the mean error here is 18.77%. If we add the time-varying base delay into Mahi-Mahi or something that we call as a CellReplay heavy, it brings down the error to 16.76%. If we further add the PDO interpolation, as we've done in our full CellReplay systems, we managed to bring down the error further to only 5.68%. Next, we also evaluate how different ABR algorithms perform over CellReplay and Mahi-Mahi. Specifically compared three ABR algorithms: buffer-based or BB, rate-based, RB, and BOLA. We stream 4K videos and evaluate the startup phase, which consists of the first 10 frames when the video starts. This is the result that we got with Mahi-Mahi. As you can see here, BOLA and RB seems to have pretty similar bitrate and are the best in this test. However, in the reality, over the live network, BOLA has a much lower bitrate, and its bitrate is more comparable to BB. CellReplay still suffers from inaccuracy, but it is closer to the ground truth. We later found the reasons of this bias. ABR algorithms are typically reactive, and its decision is affected by the measured throughput based on the video channel that it downloads. The estimated bandwidth reported in Mahi-Mahi is much higher compared to the real life, which is not surprising, as Mahi-Mahi tends to overestimate the available bandwidth itself with its saturated workload. In the paper, we also tested other conditions, such as under non-ideal stationary conditions and accuracy under mobility. So, as conclusion, CellReplay is a step towards a more faithful record and replay network emulation for cellular networks. The main problem that cellular network domain has is that its performance somehow depends on the user's workload. And our approach is to record using light and heavy workload and replay them using the interpolation. You can use CellReplay for your research in this repo. And CellReplay is also built on top of Mahi-Mahi, so if you already use Mahi-Mahi, you can easily use CellReplay. And this repo also includes 5G traces collected across a wide range of conditions, so you can start evaluating your application over CellReplay. And thank you for your attention.